Now I'll leave them on just in case someone shows up. Hello. Is Shay going to be there today? It's not going through. She said she wasn't going to be there today, but since she wasn't there last time, that was supposed to be today. Excuse me. All right, let's open up here. Get started. So next Tuesday, we're going to meet here at 1 o'clock, get in the car, and head out to Imperial. Do our lab out there with Shannon. Probably don't know Shannon Lieber, do you? Sorry, do you know Shannon Lieber? Probably not. She played volleyball here. Not this past year, but the year before. Year before that. Very good libero. Really a very good outside hitter as well, but never convinced the coach to play her outside. Cost us probably 2 dozen games, but that's okay. Never listens to me around here. All right. We are moving to the last section of heat and temperature thermo chapter. It's called thermodynamics. We've got this great picture of a steam engine. Great picture of a steam locomotive, which is a thermodynamic engine, and it runs it runs because of a process, thermodynamic process that converts heat into pressure, pressure into movement, and of course movement is kinetic energy. And we're going to learn about how this is done. We're combining a bunch of the stuff that we've learned so far about heat and temperature and internal energy and pressure. So we've actually already learned the 0th law of thermodynamics. Should I turn on my thing here? Up on the screen too, Baron. Oh, there it goes. Okay, so we've already learned the 0th law of thermodynamics, which is the law that says if you have one thing at a temperature and it's in thermal equilibrium with another thing, and those two things are in contact with a third thing and in equilibrium with it, then the first thing's in equilibrium with the third thing. In other words, if things are touching each other for a long time and they come in thermal equilibrium with each other, then they're in thermal equilibrium with everything else they've been in contact with. It's just a matter of, it's a very simple idea. And then that's the zeroth law of thermodynamics, because they actually decided it was important enough to add into the laws of thermodynamics after they made the first and second laws of thermodynamics. The first law of thermodynamics is this one, and it's really quite straightforward, actually. Essentially what you have is the change in internal energy, which we're going to call delta U of a system, is equal to the amount of heat flowing into or out of the system minus the amount of work done by the system. The minus is important, and the work done by the system is important. Also, they say that it's the net heat transfer into the system minus the net work done by the system. So Q is positive when the energy is going in, and if the energy leaves the system, then Q has to be negative. For the work, that's work done by the system. So work is positive when the work is being done by the system, or the energy is leaving the system to do the work. But if something else comes along and does work on the system, then that work becomes negative. And so that's why the signs and the wording of this are so important. There are actually different versions of this law where they define the W and the Q differently, and then the signs become different. Most of them have it written this way, but it does, those words and those signs do matter quite a bit in that. Here they have a representation of this. You have Q, heat coming in to the system. The system has a internal energy that is changing because heat is coming in, and work that is leaving, okay, the system. So in this case, they also make a definition that says that kind of defines those signs. So work or heat in minus heat out is going to equal the Q here. It's going to equal that heat in essentially. And work out minus work in is going to equal the work. So let's look at an example using this here. We're going to suppose we're going to suppose there is heat transfer. So there is a Q of 40 joules to a system. So that's heat going into the system, so that's going to be a positive 40 joules. While the system does 10 joules of work. If the system does the work, it's positive. If the system receives the heat, it's positive. So both those numbers are going to be positive in this problem. Later, there's a heat transfer of 25 joules out of the system. That will be negative. While there's 4 joules of work done on the system, that will be negative. So now we've got heat in, work out, and then heat out, work in, right? Both the first ones are positive, both the second ones are negative. And they want to know what is the net change in the internal energy of the system. Well, you could use this stuff up here to do that. You could calculate your Q by taking the Q in and subtracting the Q out and getting the total Q, and then calculate the work by getting the work out minus work in. Notice that these are opposite because of their definitions in the law. But if you use these definitions, then you can go ahead and just use them in the equation after you've calculated Q and W. Also, you could just do it separately. You could do positive Q and positive work and plug them into the equation and get the net change. And then you could do it with a negative Q and a negative work, and it would change the equation because you've just changed the signs in the equation. But it would still work out, and then you would add together those two changes, and you would get the total change. So it looks like they're going to use the first method where they take the the heat in minus the heat out, and they get 15 joules total heat. They're going to do the work out minus the work in, 6 joules total work, and they're going to plug them into the equation. And it's a good way to do it as long as the law is this version of it. If somebody comes along and gives you a different version of the first law of thermodynamics, then you might get screwed up a little bit. But in part B, they want to know what is the change in the internal energy of the system when a total of 150 joules of heat transfer occurs out of the system and 159 joules work is done on the system. So if the heat transfer is out of the system, that's negative or positive? No, out of, remember, heat is positive when it goes into the system in this case.
I see what.
Right? And then work is 159 joules done on the system. That's also going to be negative. So you just plug these two in as negative numbers. Or you can use the other thing where you have a zero work. You'll have a zero to start with, and then you'll subtract off that one. And that's what they're going to do here. They're going to have a zero. No, they don't actually do it. They do it my way here. They actually just make Q a negative number and work a negative number. So in the first part they do the difference thing. In the second part they just assign them values because that is also valid. Here they show pictures for each of those. And it's a good idea to draw pictures for thermodynamic problems because sometimes it's really confusing to figure out if energy is going into or out of a system. But again, I think that the law is confusing because it has a Q minus a W. Personally, I prefer the law where the Q and the W are both positive, and you just decide what signs they are, whether they're going in or out. So when the work's going out, you call it negative, and it becomes a minus W. And in that case, and I'll show you what that looks like when you do that version of the law. In my ideal world, the law of thermodynamics, that first law of thermodynamics looks like this. Change in internal energy of a system equals Q plus W. And you have a system like this, where if the W is, or the Q is going in, then that's positive. It doesn't matter if it's W or Q. Because what are these things? They're just energies. So if the energy is going into the system, it's going to increase your internal energy. So it's going to have to be positive. If it's leaving the system, then it's negative. Well, what does that mean for Q? For Q, if it says the system absorbs so much heat, or so much heat is transferred into the system, or something heats up a system, then that's going into the system. But if it says the system loses heat, or the heat dissipates out of the system, or the heat leaves the system, or the system is cooling off and loses so much heat, then those are heats leaving the system and they're going to be negative. For the work, if it says the system does work on something else, that means the system is giving away its energy in the form of work. That means it's going out, it's negative. But if it says something else does work on the system, something comes in and increases the pressure of the system, or moves the system, or does something inside the system that is going to be equivalent to work being done on the system, then that's positive work, because you're increasing the energy of the system by doing work on it. And so that's what I mean by the two different versions. This is the other version of the law, which to me makes a lot more sense. There's a lot less confusion with it. All you have to do is draw the picture, and if it goes in, it's positive because it's increasing your energy. If it goes out, it's negative because it's decreasing energy, end of story. It's the same rule for both the heat and the work, and you don't have to think of different rules for the heat and the work, and why is there a minus sign in this equation. You know, it's different strokes for different folks. You know, for me, I'm much better at remembering concepts than I am at remembering equations. So I like something that's very conceptual, that makes sense. So anyway, not everybody's the same as me. Well, human metabolism. This is a great equation for human metabolism because it kind of shows you what human metabolism is about. Your human metabolism is all about this delta U thing, and the Q is essentially what you eat, and the W is essentially the exercise that you do. So the Q, food coming in, energy coming in, the work you do, energy going out. And that's why this equation is favored by a lot of people, because it makes it easier to understand things like human metabolism and things like this. Because the negative, you know, the work, that's energy leaving your body, that's fat leaving your body, whatever. But to me, energy can be positive or negative anyway, so it doesn't make any difference to me. I can care less. Here they're actually going to add on one other energy. They're going to split the Q. They're going to split the Q into heat leaving your body and food entering your body. which is also true for a human body, and that's fine. But the heat here is what is called the resting metabolism. That's how much energy your body burns up just sitting still. And it essentially leaves your body in the form of heat. And this is where I find it just confusing anyway, because now the Q is negative, leaving your body, even though it's positive up here. You have to put in a negative number to make the equation work properly. So anyway, just goofy things, I guess. So now how are we going to apply this to some engineering? Again, we're going to draw a picture, and we're going to draw a very simplistic view of what we call a heat engine. A heat engine works very similar to the human body, where you add energy in the form of heat instead of in the form of food. But it's in the form of heat, and then there's some kind of process within the engine that converts some of that heat into work that leaves the system. But then there's always some residual heat left over that has to leave the system. Now, if you've ever opened the engine compartment of a car or been near a locomotive that's got its engine running, you'll know that there's heat coming off of them. It's really quite obvious. That actually is a very necessary part of this process. This Q out is extremely necessary. If it doesn't happen, the engine cannot work. In fact, the more efficiently this heat leaves the engine determines the efficiency. It actually is a big determiner in the efficiency of the engine overall. This is why we have things like radiators on engines that are using these mixture of complex alcohols and everything to do the cooling in your engine, because you want that cooling to happen very well. Here is one version, a very simplistic version of a heat engine. You have heat coming into a piston filled with a gas that is sealed off, and on the end of the piston, on the end of the cylinder, there's a piston. So this is the cylinder, this is the piston. As you heat the gas, it expands according to the ideal gas law. There's a pressure. As you heat the gas, there's an increase in pressure. The increase in pressure forces the piston to the right and increases the volume of the cylinder, of course, in the meantime. And that piston pushes some kind of a rod which is connected to some thing that can turn around and around, or whatever, your wheels, your drivers, whatever they're connected to. It can be transmission, whatever. But then at the end of that stroke, at the end of that push, this thing is going to have to return back to where it started, because if it doesn't, then it can't push again. Well, how do you return it back to its start? Well, you cool it off. How do you cool it off? Well, you just let that heat get out, or you draw the heat out using fluids, like from your radiator or something like that. And that's ideal. So then you begin to start the cycle over and over again. So let's look at a very simple process that is going to help us to understand how we do this, the math and the science of these engines. And we're going to call this the isobaric process. This is a process where the pressure is not going to change, but we're going to let everything else in the gas that is trapped in this piston change. So what kind of things do we have? Well, think about the ideal gas law. You have QV equals, so not QV, P, I can't remember, PV equals MRT, right? NRT, NKT, whatever. You can be either one of those two, right? NRT or NKT equals PV. And so those three variables are the things that we're going to allow to change, except for, in this case, the pressure. We're going to hold the pressure steady. Well, how do the other things change if the pressure doesn't change? Well, you have two things that can change on either side of the equation, so they can both change, right? In this case, we're going to let if the volume, if we increase the temperature, for example, we'll allow the volume to increase with it, so that the pressure doesn't change. And then, essentially, what that means is we kind of pull up this piston inside the cylinder while it's heating up, and the pressure won't change. Or if the pressure changes, we change the temperature. If the pressure goes down, then we turn the temperature down, and then the pressure won't. Then the Sorry, if the volume goes down, because we don't want the pressure to change at all. Right, there we go. So that's called an isobaric process. And when you have an isobaric process, and you have this pressure thing always remaining the same, the work actually becomes the pressure times the change in volume. And that's something that they're showing you the process up here, the mathematical process. Okay. This equation here, work equals pressure times delta V, to the change in volume, is an equation that kind of defines the parameters during an isobaric process. Now that could be useful in an engine, to have this ability to allow the volume to change without its changing the volume to change without it changing pressure. It could be useful, so we want to know as much as we can about it. If we put it on a diagram where we have pressure on the y-axis and volume on the x-axis, this is what it would look like. You would go from one point in pressure to the same point in pressure, so it's at the same level of pressure, but you would be changing volume. And the amount of work being done would be the pressure times the change in volume, which would be actually the area under this curve, the area under this line. Well, that's convenient, because when you're finding the area under curves, that's calculus. That's just doing integral, and that's going to be helpful for us. So that if we have the area under an actual curve instead of just a straight line, we can actually calculate that as well using calculus, which is what they're showing here. Which is nice, because eventually, because there's no such thing as having a perfect isobaric instrument. It just can't be done. You can get pretty close, but in real life, you're going to have things that are going to be changing all three variables. So we're going to need to know how to do this eventually. Okay, so that's isobaric processes. What happens if we have two isobaric processes, right? And then going between them, we have what we call isochoric processes, which is where the volume doesn't change. How much work is being done? If the work is being done is the area under the curve here, but you have two of them happening, well, you can take the difference between the two, right? So you can start to do some simple math and other things like this. What if you have a thing that goes around and around, then it's the area inside, because you take the area under this top half of the curve, which would cover this part, and then the area under the bottom half of the curve, subtract it off, would give you just the area inside. And so this actually has led us to, and this is kind of a shorthand version of a very long calculus proof, but essentially what we've shown you here is that we can calculate how much work an engine does by calculating the area that is inside of the cycle that the engine goes through as it goes through its repeated cycle that it goes through as it changes volume, changes pressure, changes temperature. That's useful. So let's do a simple calculation of work where we have figure 1512, which I'm going to assume is the next page. There it is. Nope, that's figure 15. So figure 1512B, which is this one here. So in this one here, we have a process that is a cycle. It starts where it finishes, in other words, that is going to be isobaric, pressure's not changing, then isochoric, volume's not changing, then isobaric, pressure's not changing, then isochoric again, it ends up where it started. And so it will go around and around and around and around, just like an engine does. An engine goes through this thing where you heat up the piston, you heat up the cylinder, the air inside the cylinder, or the gas inside the cylinder expands, changing pressure. And by pushing on the cylinder, it does some work, so it releases some energy in that situation. And then it cools off so that so the piston gets smaller again in volume, change in volume, and then you heat it up again and it expands again. And it does this again and again and again. It goes through the process again and again and again. So it's very much similar to this. And we want to be able to calculate the work that is being done in this process. Well, of course, you have work here under this curve, which is this big rectangle, and you have work under this curve, the small rectangle. Well, one of these is work being done, and one of these is work being done. One of these is work being done by the cylinder. One of them is work being done on the cylinder. And you really hope that the work being done on the cylinder is less than the work being done by the cylinder, because you want to get some work out of it, right? And so the bigger one is the work being done by the cylinder, the smaller one is the work you do on the cylinder. That's to make it small again. And then you have the area inside of the loop, or the area inside of the cycle here, is the work being done by the engine on its surroundings, making the thing roll or whatever. So they want you to do that, and how do you do that? You're just calculating the areas of the boxes, right? Not that hard to do. However, in the real world, it gets quite a bit more complicated, and we have things like this, where instead of a nice flat line box, we have curves, and these two curves are representations of two other types of things that can happen: isothermal and adiabatic processes. In the isothermal process, delta T is equal to 0, so the temperature doesn't change. And in the adiabatic process, the heat flow is 0. No heat goes in or out. Okay? How do you achieve a process where delta T is equal to 0? Well, the best thing to do with that one is to make the process happen fairly slowly. No, fairly. Slowly. Think slowly. So, if, for example, if you add heat to a system and allow it to expand slowly at the same time, the heat that you're adding to the system won't increase the temperature, it will just increase the pressure if you're allowing it to expand. That kind of thing. The other one, the adiabatic process, the best way to make that happen is to make it happen extremely quickly so that the heat doesn't have time to flow. Because it takes time for heat to get through the walls of a cylinder, for example. And if you just make it happen extremely fast, then it becomes an adiabatic process, usually. We're very close to it. So, now, reversible processes. Can processes be undone when they're done? Yes, ideally. A perfectly adiabatic process can be reversed, and it can be reversed completely, reversed perfectly. A perfect isothermal process can be reversed perfectly, as long as the original process was perfect. But are they ever perfect? No, they're never perfect, at least on a macrocosmic scale. And so you're always losing some energy in these processes. If they were perfect and you could reverse them, you wouldn't lose any energy, and you could have a perfect engine that would run forever. You never have to add any heat to it. It could just use its own heat and its own process to keep itself going. That's not possible. And that actually is something that has actually led to the second law of thermodynamics, which essentially says that no processes are irreversible. That everything eventually dies off and leaks out energy in forms of friction and just residual heat loss and other things. But anyway, we've come to this point now that we've been able to define 4 types of processes that we can hopefully make use of. Isobaric process, which is a constant pressure process, where the work is equal to P times delta V. The change in volume is the work being done, essentially. The pressure causes the volume either to get bigger and push outward on its surroundings, that's work, or causes the volume to get smaller so that the surroundings are pushing inward on the engine, and that's work being done on the system. Isochoric process, the volume doesn't change, so there's no pushing going on, so there's no movement, so there's no work. Isothermal process, the Q is equal to the work. The amount of heat you put in goes directly into expanding the object, no temperature change, so that's isothermal, and the heat and the work are the same amount of energy. And then the adiabatic process, there's no heat transfer, so Q equals 0. They don't talk about what the work is equal to here, but we can do that later. In real life, none of these processes really exist. in the macrocosmic world. In the microcosmic world, they do, like on the levels of atoms, molecules, and things like that, subatomic particles. But in the realm of anything much bigger than that, there's always some loss of energy somewhere, and nothing can be done about it. So what does that lead to? That leads to the second law of thermodynamics, and I have this great picture here of the melting ice on the Arctic in the summertime, right? The second law of thermodynamics essentially says that everything in the universe tends to become more disorganized and less, you're always losing energy, essentially. Ice is a great example of this, because when ice is in its crystalline form, it's very organized. However, it never remains as ice. It always eventually melts and turns into disorderly liquid. Liquid is just all over the place. Wherever it wants to flow, wherever it needs to flow, it flows. And then it turns into a gas, and it's even more disorganized. It's random as all craziness when it's a gas. It can even become a plasma, which is even more disorganized. But this is just as true for ice as it is for the entire universe. The entire universe, at its very beginning, before the Big Bang, was a very organized piece of matter, or energy rather, and we don't even know the form of it. We're not even sure that we could even fathom or understand what kind of form it was in. But when the Big Bang began, that energy began to spread out and become more random, and began to disorganize itself. Now, in the process of doing that, it created different pockets of order, stars and solar systems and planets and comets and other things that are kind of like organized energy in the form of matter. Matter is a form of organized energy, but there is no form of matter that was created in the Big Bang that didn't immediately begin to disorganize ever since, and is still disorganizing. All stars are, burning out. They're losing their energy, and instead of having an orderly fusion reaction going on, that's creating this density and this energy in this star, it's releasing things out into the galaxy, into the universe, in the forms of plasmas, in the forms of gases, in the forms of free particles and radiation that are just kind of bouncing around randomly. And every single process in the universe always always creates more disorder than order. There's no way to organize without disorganizing more. And you say, well, what if I clean my room? Take a very simple example. I clean my room. Well, yeah, you clean your room, and you have now ordered your books, and you've ordered your bed, and you've ordered your dirty laundry, and you've ordered the dirt that was in your carpet into the vacuum cleaner. But every single act that you did released heat into the universe. As you worked, you were releasing heat. As your muscles were going, you released heat. And in fact, your muscles were breaking down while you were releasing heat. And you were breaking down fat while you were doing this work. And all the processes in the vacuum cleaner, the electricity going through the wires, the motor spinning, all those things are releasing heat. And heat is disorder. Heat is speeding up all kinds of things and making them more random. And you can actually measure how much order you created by cleaning your room, and measure how much disorder you created while cleaning your room, and discover that the disorder was greater than the order. And it's a great excuse for not cleaning your room, right? Say, Mom, you're contributing to disorder when you ask me to clean my room. It's true of everything, and that's the really interesting thing. It's even true of thought. Thought, being a biochemical process, actually, you say organize your thoughts. Well, yeah, you're going to organize your thoughts by disorganizing the universe. There's only a finite amount of energy in the universe. And so eventually, all of the energy in the universe that can be disordered will eventually be disordered, and there will be no more energy to do anything else. It's a long ways away. We've still got a lot of energy organized in a lot of places, so that we're not really worried about that happening. But this idea that the order of the universe will eventually become completely disorganized is what we call the heat of the universe.
And it essentially comes from this idea that there's no such thing as a perfectly reversible process. Because every time you go through some kind of thermodynamic process, every time you do anything, which is some kind of thermodynamic process, everything is a thermodynamic process. Anytime you do anything, you are going to release more energy in forms that cannot be recovered than you're going to organize energy. And that's what irreversibility is. When I was in must have been my junior year, I was taking a thermodynamics course, and we had to do a presentation about the second law of thermodynamics, actually. And our presentation was about thought. There are actually many research groups out there that have done research on how thinking and how reasoning and using logic how you can quantify the loss of this energy loss to the universe. This idea is called entropy, actually. You've probably heard of this before, probably in chemistry. And they talk about it a lot in chemistry in a way that I'm not sure I completely agree with. They try to make it sound a lot more, quantifiable than it really is. You can quantify it, you can measure it, you can calculate it. Well, you can calculate it, you can't necessarily always measure it. But anyway, it's a very interesting idea. So here is a more specific and actually a little more kind of chemistry definition of the second law of thermodynamics. And they're going to show us several expressions of this. Heat transfer occurs spontaneously from higher to lower temperature bodies. So higher temperature bodies, which are more random, release their heat to lower temperature bodies, which are more organized. And what is that going to result in? More disorder, right? So what they're saying here is that nature tends to disorder itself. But it never spontaneously goes in the other direction. Hot water never freezes, just spontaneously. Okay? You have to make it freeze by putting it into a refrigerator, which of course requires a lot of work to make that work. So how do we take advantage of this in thermodynamics? Well, we create something really hot, and we put it nearby something kind of cold, and we put our heat engine in between. Because we know that nature is going to force that heat to go towards the cold. And we're going to take advantage of it by running it through our engine, so we can use it to expand a gas or make something turn or whatever, right? And so we take advantage of this idea that this law. What's another way to state this? It is impossible in any system for heat transfer from a reservoir to completely convert work in a cyclical process in which the system returns to its initial state. What they're saying here is that you cannot completely to turn all of the heat flow completely into work. Some of it has to go to the cold reservoir. And in fact, through some mathematics, they were able to actually figure out exactly how much of it has to return to the cold reservoir. There has to be at least a certain amount that goes to the cold reservoir. And as a result, they were able to actually determine the most efficient engine. If you only let that much heat go to the cold reservoir and use all the rest of the heat to turn into work, then that's as efficient as you can get. And they were able to figure that out. First of all, we have to define our efficiency. The efficiency of an engine is going to be defined as the amount of work you can get out of the engine compared to the amount of heat you pull out of the hot reservoir, right? So Q hot, QH is the heat that you pull out of the hot reservoir. The work is the work done by the engine. Another way that you can express it as, since the work is equal to the difference between hot and cold, you can express it as 1 minus the heat going into the cold reservoir divided by the heat coming out of the hot reservoir. So we have now a definition for efficiency. So let's look at an example of a coal-fired power station. It's a big heat engine. You're burning coal. You're heating up water, turning it into gas. Use that gas to turn turbines. As the gas turns the turbines, it cools off, and turns back into a liquid, and then you heat it again, right? So in this particular power station, there's 2.5 times 10 to the 14 joules of heat that comes from the coal, and 1.48 times 10 to the 14 joules of heat transfer into the environment. Okay? So what is the work done by the power station? The work done is the difference between these two. Because this is how much heat goes into the station, this is how much heat comes out of the station. Everything in between is heat that's going into work. There's, what is the work done by the power station? You take that difference, right here they say that, and they give us a number. Work being done, 1.02 times 10 to the 14 joules. Then they want us to calculate the efficiency, which is just that number, the work done, divided by the heat coming out of the hot reservoir. So we plug in those two numbers, we get 40.8%. That's actually extremely high for a coal-fired power station. Usually they're not quite that high. And then in C, they want to know how much CO2 is put in the atmosphere. So they calculate how many kilograms of coal comes from this amount of joules of coal, how many kilograms of coal are required in this joule. They tell us how much it is. They tell us how much it creates. And then we use this chemical equation to figure out how much CO2 goes in the air from that, amount of coal, essentially doing a little chemistry. Do you remember how to do this stuff?
No.
Okay, well, you have the equation here. Carbon plus oxygen, O2, is equal to CO2, right?
Yeah.
The carbon, if you look it up on the periodic table, has 12, here it is. It's 12 kilograms it's got a 12 on the periodic table, right?
Yep.
And the 12 essentially means how much weight it is per mole. That's how many grams per mole. We're just going to use it in kilograms instead of grams. It doesn't really matter, it's just a ratio, right? In the oxygen, turns out to be 16, but there's 2 of them, so they add in 2, right? And all of it becomes CO2. So all of this, for every kilogram of stuff you put in over here, you're going to have, so if you put in a kilogram of, if you put in 12 kilograms of carbon here, because there's a 12 next to it, and then 2 16s, which is 32 of oxygen, and then you're going to get out the sum of that in CO2. It all becomes CO2, essentially. Okay? And so that's all they've done here.
Where do we get the 2.5 times 10 to the 6?
This one?
Yeah.
That's a number that they give us. 2.5 times 10 to the 14 joules of heat transfer from the coal.
Okay.
So you get this. This is the amount of energy that they get from their coal every day. And if from 10 to the 6. That's the wrong one. This one is actually given to us in the problem at the beginning of the yeah, right here. Assuming that 1 kilogram of coal provides 2.5 times 10 to the 6 joules. So down here, for every kilogram of coal, this is what we get. And this is how much energy we use, so you divide these two to get the amount of kilograms.
Okay.
And then we're going to use the ratios from this stuff here. So for every 12 kilograms of carbon, of coal in other words, you get 44 kilograms of CO2, right? The oxygen just comes from the air around the air around the building. So this is how much coal they have to start with. They multiply by this ratio, the 44 over the 12, which they got from the chemistry. And then they get 3.7 times 10 to the 8 kilograms of CO2. And that's quite important because they have restrictions. They can only put out so much CO2 every day by the EPA laws. And then so they have to actually make sure that they're scrubbing a certain amount of this. And to scrub it, essentially what they do is they put it through a big electrostatic filter that separates the CO2 from the surrounding air, and it traps it. So it traps it inside of a filter, actually. And then the filters are taken out. It's an electrostatic thing. So that is efficiency. The next thing they're going to talk about is the Otto cycle. Otto was the guy that invented the 4-stroke engine. He also invented diesel engines. We'll get to this when we come back. I'm going to take a little break for about 10 minutes. But this is now, we're getting into more practical things. All right, be back in 10. Okay, the Otto cycle. So, this is kind of what it looks like. Dang it, it's my left string is dead again. Why does it always do that? Whatever. Let's try. Okay, got it working. Just come up on the screen back here. We're good. Okay, good. So anyway, the Otto cycle. Essentially, it's called a four-stroke engine or a four-stroke cycle because there are four things that happen, and these four things do not necessarily exactly correspond to the four different things on the PV diagram, but they're pretty close. Essentially, what you've got up here is your piston, which is this area up in here. Or sorry, your cylinder, this area in here with this piston in it. Piston is connected to this rod. The rod is connected to the camshaft. This camshaft goes down the length of the car, so into the page, or out of the page. And that camshaft is essentially the long axis of your engine block. And that camshaft connects to your transmission generally, which connects to your wheels. So, the four strokes are, this first one we call intake, where you have these valves up at the top that open to allow air to come into the cylinder, and this piston comes down and draws the air into the cylinder. Then you seal up the valves up here, the two little red things, and you have the compression cycle where this thing has now gone around and it's squeezing the air up here. And while you're squeezing the air up here, oh, by the way, this is not just air, but it's also fuel. These valves go to the carburetor or the fuel mixing, whatever, the fuel injection, whatever. So you're getting air and fuel inside these valves. So anyway, you got fuel and air in here, and then when you compress it, then you either have a spark that causes combustion, or the power cycle, or in the case of a diesel engine, it just ignites itself from the high pressure. As it ignites, of course, all that fuel and air in there combusts. It explodes, and as it explodes, it increases the pressure here and pushes the piston down, and you get this huge power stroke where the piston is thrown down and it forces this camshaft around. And I mean, the thing that's a little bit weird about this is the camshaft is not the same, doesn't have the same radius in every one of these cycles because it has an oblong center to it. The camshaft, that's why it's called a camshaft, because it has a cam on it. But anyway, as the thing explodes and expands, you get your power stroke, and then at the end of the power stroke, you open up this other valve over here, and it releases all of the gases that are in there now that come out as a result of the combustion, usually CO2 and some water and some other things like this. So then it starts all over again. It goes back up, goes back around, comes back up to here, and fills with air and goes through the cycle again. So there are your four strokes in this cycle. And ideally, you would have two adiabatic curves here, followed by two isochoric transitions where the volume doesn't change. It's not exactly what happens, but you can kind of see that the volume's not changing up here very much, here and here. But the volume does change quite a bit here and here. You have a small volume, a tiny volume here, and a big volume here. And so that's kind of where the transitions take place. Like I said earlier, it's not exactly the way it is, but it's okay. And it is still a thermodynamic process. You have a place where it's hot and a place where it's cold. Where's the hot and the cold? Well, the hot is inside the cylinder, and the cold is everything outside the engine, right? And then where's the work happen? The work happens down here as the piston pushes on the rod and turns the camshaft. Well, of course, we can calculate the amount of work done by calculating the area between these curves require a little bit of calculus. But it can be done. And then you can calculate from the work there, you can calculate also the efficiency of the engine and everything else. Now, what would be the most efficient engine, theoretically speaking? The most efficient engine is what we call a Carnot cycle. And if you've ever seen one of these toys before, this is actually built on this principle of the Carnot cycle. It's called the drinking bird. And essentially, you've got this red stuff is essentially some alcohol, 100% alcohol, inside of a vacuum-sealed bulb. And then you put a glass of cold water here. And the cold water, you put the nose of the bird in the cold water, and it cools off the glass, which cools off this alcohol. As it cools off this alcohol, the alcohol actually changes its density, becomes more dense, and it changes the balance of this thing, and it causes the bird to stand up and not have its nose in the alcohol anymore. Once its nose is not in the alcohol, it warms up again, and the alcohol expands, and as it expands, it goes up this tube, and it causes the bird to fall over again and puts its nose in the cold water. And then it cools off again, it contracts, the alcohol contracts, and goes back. So you're causing work to be done on the alcohol by changing its volume, by putting it in cold and then allowing it to warm up and then putting it in cold. But it does this in a drinking bird. As long as you keep this water cold over here and the room is warm compared to the water, this will keep going and keep going and keep going. Of course, you have to keep the room warm and you have to keep the cup cold. But it's a really good example of a Carnot engine. Well, what does the diagram look like for a Carnot engine? It looks very similar to the Otto engine, but not exactly the same. Instead of having these two isochoric sides to it, it actually has an adiabatic compression and an adiabatic expansion, and isothermal arms on the top and bottom, where the heat does not transfer out. So it's the most efficient engine there is, theoretically speaking. Theoretically speaking, you cannot draw a cycle on a PV curve that has more work done for the amount of heat lost. And so, what is the efficiency of a Carnot? This would be, of course, the Carnot efficiency if you calculated it. But what would be the efficiency? You'd have to have. You'd have to be able to make a really cold and really hot, really cold and really hot temperature difference. Try to get this as efficient as possible. Of course, there is a limit to that. You can only be at absolute zero, for example, and so on and so forth. But it turns out that there is a theoretical limit to it. Let's look at a nuclear reactor here. Nuclear reactor, pressurized water at 300 degrees Celsius. You can get higher, but it's kind of hard to get much higher. So, and it's at pressure, which is what allows it to get so hot. This is what a nuclear reactor looks like. You have your nuclear section here, which is contained in a big containment building, a containment structure, usually completely concrete and steel. And inside of here you have your uranium, your plutonium, whatever it is that's doing the reaction. And it heats up the pressurized water here in the pressure vessel. And as it heats up this water, it gets up to 300 degrees, this water goes into another water container where it turns the water into steam. The steam leaves the reactor. Notice that you don't have any lines that are connected directly from nuclear reactor to the outside. These are completely sealed so that they never come in contact with each other. They come in thermal contact, but they don't exchange any kind of materials with each other. So that the steam out here is not is low radiation instead of high radiation. This stuff is high radiation. But anyway, you get low radiation steam out here that is easy to shield, and you put it through the turbines. The turbines turn. As they turn, the gas cools. It turns back into a liquid, and it goes back into here to get heated up again. They also have another cooling, you also have to have another cooling method because this water in here is so hot, the steam gets so hot that you need to cool it even more in order for it to turn back into a liquid so you can put it back in here. And so in the case of the reactors here in Nebraska, they have another system where they bring in river water and run it through here. And the Missouri River cools down the steam to help it condense. In other places, they have cooling towers where they run the water through and the cooling tower cools off. The cooling tower just is like a radiator, just like a big radiator. So anyway, that's how it works. So what is the efficiency? If we consider this to be a Carnot engine, for example, if this had the maximum efficiency, the most efficient it could be, it would be a Carnot engine. And we're using water, so the coldest the water is going to be able to get, it turns out, is 27 degrees Celsius. If it gets much colder than that, it becomes difficult for it to, you start dealing with other problems. You don't want icing, for example, in your water, so you have to keep it at a reasonable temperature. Also, you don't want to have to cool it using a refrigerator, because then you're detracting efficiency. So 27 degrees Celsius is essentially room temperature. It's normal temperatures. So you keep it down to temperatures of the outside. If you can get it down to normal temperature of the outside air, then it's as efficient as it's going to get. Plug in those things and you're getting a 47.6% efficiency. Usually nuclear power reactors are quite a bit lower, 35%. That's actually pretty good too. 35% is pretty dang good. Here they show a reactor with its cooling towers, and you can see that there's a lot of steam coming out of this as it cools off. The cooling towers have multiple cooling systems in them, but essentially they just pump water into the generator area, and that water again becomes really hot. They bring it out, and then they run it into channels in the cooling tower, smaller and smaller channels that allow it to evaporate easily. And as it evaporates, it carries away a lot of energy. But just because you see these towers around doesn't necessarily mean it's a nuclear power station, because normal coal-fired power stations often use cooling towers that look just like this. They're not usually quite as big, because coal-fired power plants do not dissipate nearly as much energy as a nuclear reactor does. A nuclear reactor that's the same size as a coal-fired power plant can create a lot more energy. It can create a lot more heat and a lot more electricity. So it takes a big coal-powered plant to need cooling towers that big. There are some, but it's just not very common. So anyway, here they're just talking about different things that can cause, energy loss. Essentially, that can cause inefficiency in engines. There's lots of different things. There's so many ways to lose heat inside of heat engines, and there's so many different kinds of work that are done by heat engines that's work that's lost. The work due to friction, for example, inside the generators, inside the turbines. That's all energy that's lost and can't be turned into electricity because it's lost in the process, not in the thermodynamic process, but in friction processes. Leaks in the system itself, actual fluid leaks, steam leaks, those cause problems. And that's what power plant operators essentially spend their time doing is monitoring those things, fixing those things, and maximizing the efficiency of their power plant. Efficiency means money, essentially. Particularly important in a place like Nebraska. We're the only place in the United States that has a public power system where the power companies are owned by the people of the state. So there aren't any companies or CEOs that are making huge paychecks off of the people. That's great for Nebraskans, because we're paying about 1/10 the cost that they're paying in California for electricity, and we're paying about half what most other states are paying. So it's great for us to have very efficient things, because that comes directly to our power bill. In other places, it doesn't really affect the consumer so much. It just increases the profit margin for the companies. but anyway. Here they talk about using heat pumps in your home as essentially like a refrigerator, an air conditioner, or and that's what air conditioners are. Air conditioners are essentially a heat pump that where instead of you burning something, heating something up, creating that hot and cold reservoir to do work, you actually do work to force the energy to go from the hot to the cold or the cold to the hot reservoir. In the case of the air conditioner, you have an air conditioner in the house and you do work on the air conditioner. You plug it into the wall, you turn some motors in the air conditioner that actually condense a gas, and it's like making a heat engine run backwards. So that instead of the heat flowing from the hot to the cold and doing work, you're doing work on the engine and forcing the heat to go from the cold to the hot. So the cold reservoir is the cold reservoir is where you want to cool things off, and you force heat to go from inside your house, which is the cold reservoir, to outside your house, and you cool off the house even more. That's how refrigerators work. It's how air conditioners work. It's how lots of things work, actually. But you can also run your air conditioner backwards, essentially just turn it around in the window if you have a window air conditioner in the wintertime, and you can actually draw heat from the house, draw heat from the outside into your house. You say, how can that be? It's colder outside than it is inside. But there's still heat. There's still thermal energy in the air outside. And using that air conditioner backwards, you can actually heat your house. It's not very efficient with a window air conditioner, but if you have a big one, which some houses do, you can do it. It's also not very efficient if your electricity is expensive, and it's not efficient if it gets too cold outside. If it gets so cold outside that there's just very little internal energy in the air outside, you're not going to be able to warm up your house very much. It can only warm an average heat pump can only warm your house about 10 degrees warmer than it is outside. So when it's 60 degrees outside, 50 degrees outside, it's great. But when it's 30 degrees outside or 20 degrees outside, they don't work so well. They are a very efficient way to heat, though. They use very little energy to heat. So heat pumps are essentially refrigerators, air conditioners, and they can be used both to heat and to cool. The interesting thing about them, though, is that it still does require an inside and an outside, or a hot and a cold. So a lot of people think that if they open up their refrigerator door, they're going to cool off their house. Well, not true, because when you open up your refrigerator door, you're actually connecting the hot and the cold reservoirs. So you're going to get some transfer of heat, but as the refrigerator turns on to try to make up for that loss of heat, that heat transfer that's coming from the house into the refrigerator door that you've opened, it's actually going to heat up the house even more, because it's doing more work than it should. And so it doesn't really help you in the end. It actually heats up your house. But the idea is just the reverse of an engine. With a heat engine, you were heating up a gas so it would expand and do some work, and then you'd have to cool it down to start the process again. Well, with a heat engine, you cool off a gas, and then that condenses it. And to cool off the gas, you actually have to do some work. So instead of getting work out, you put work in. You actually use what's called a condenser pump, and it's like forcing fluids to go backwards through a radiator. So you have gas that you force into a radiator backwards, it cools off the gas, turns it into a liquid, so it condenses it, and then you have that condensed water, and then you allow it to go into the hot part, which is the inside of the refrigerator, and then you allow it to evaporate. Well, that means it has to be a liquid that evaporates in a cold temperature. That is why we use Freon in refrigerators and inside of air conditioners. Freon is a liquid that evaporates at very low temperatures, that is a gas normally in normal air temperatures, and it's a gas at very cold temperatures. But if you force it to become a liquid by condensing it, we're using a condensing pump and a condensing system, you force it into as a high pressure liquid, and then you take it into that cold environment and let it absorb heat inside the refrigerator and expand into a gas, and then bring it out and condense it again, and force it to condense and keep doing that, you're going to cool down the inside of a refrigerator quite a bit as that gas absorbs that energy as it expands. So instead of talking about efficiency with heat engines, we try to make a little difference. We call it the coefficient of performance. Coefficient of performance is essentially 1 over the efficiency. It's not that different. It can be calculated by taking the energy coming out of the hot reservoir, the energy that you're removing from the inside of the refrigerator, from the inside of the air conditioning house, and dividing it by the work that was required to do that. And that will give you your coefficient of performance, and it's just the inverse of the efficiency. So of course here we're going to calculate the coefficient of performance for a heat pump. What is the best one going to be? Well, of course, if a Carnot engine is the most efficient engine, heat engine, then a Carnot heat pump would be the most efficient heat pump, because it's the same thing, it's just backwards. It's going to be the same kind of deal. So the efficiency of a Carnot engine, we can actually calculate between normal temperatures and hot temperatures, right? We get efficiency for Carnot of 0.1887. If we take the inverse of that, we get 5.3 as a best coefficient of performance for a an air conditioner or a heat pump. And like I said, the work usually comes from electricity, so we often are using electrical work as our work. Not that hard to calculate, actually. It's just the current times the voltage. Well, yeah, I think it's current. That's power. It's current times voltage times time is what it is. With air conditioning in a house, they actually use their own little thing, their own little performance calculation. They call it EER, which is, I can't remember what they call it, the energy efficiency rating, I think. Energy efficiency rating, yeah. So you take the heat actually going into the cold reservoir, coming out of the cold reservoir, divided by time in hours. Divided by time in hours, divided by the work, divided by the time 2 in hours. So time 1 and time 2 are in hours. And that's the energy efficiency rating. Whatever. Yeah. Okay. So now we're all the way into entropy. Let's talk about what is entropy. Entropy in the second law of thermodynamics, disorder and the unavailability of energy. Remember, the second law says that energy in the unit, or that essentially that heat always flows from a hot reservoir to a cold reservoir spontaneously in nature. It never does the opposite. This is going to be essentially, it's going to be a thing that involves heat and temperature, where temperature, remember, is a way of understanding the internal energy. It's not a direct measurement of the internal energy, but it is part of the process of getting it, right? And heat, of course, is a flow of energy in and out of the system. And we're going to define energy, or entropy, or change in entropy rather, as Q over T for a reversible process. So this is good when the process is a perfectly reversible process. Take the heat flow divided by the temperature, and you get the entropy, the change in entropy. So remember, this is for a perfect process, a reversible process. And if you have heat flowing from one state to another in a process, or so you have your gas in a tube or something here, and you go from one state to through this process that's reversible, you're going to have some heat flow and a temperature change. But it turns out that the entropy, even for so even for a reversible process, I was just trying to see where they were going with this. even for a reversible process, you actually have a measurable change in entropy. In other words, the entropy does not stay the same, even if it's reversible. So entropy is not exactly energy. It's not exactly anything, really, because temperature is not exactly energy. That's really the bottom line here. But this thing always goes down, no matter what the process is. If you take into account everything that happens, this thing always changes, and the change is always downward. It's always negative. And it turns out that even if you don't have a reversible process, and this comes from not only theoretical but observation, it's actually the same thing. You actually get the same change in entropy. So entropy doesn't really care how you get there. It just cares that you got there. And that's because all it cares about is heat and temperature. So we're going to calculate the change in entropy of 4,000 joules of heat transfer from a hot to a cold reservoir. We have the heat, we have the temperature change. We're good to go. Sorry, we have the temperature. We don't need temperature change. And so to calculate these things, we take the change in entropy of the hot reservoir. So it's 4,000 joules going out at 600 Kelvin, and it's negative 6.67 joules per Kelvin. And in the cold reservoir, we have a change in entropy of 4,000 over 250, 16 joules per Kelvin, right? And the total change in entropy, as we add them together, is 9.33 joules per Kelvin. There is an increase in entropy for this system. And I said entropy is negative. It's actually always positive. I was wrong with that, sorry. But an increase in entropy means an increase in disorder. So, and that's why I say it's not exactly energy, because it isn't. Entropy is actually a measure of disorder. And so the more entropy you have in the universe, the more disorder you have. So every time, it doesn't matter that, neither of these change temperatures, but there was a heat transfer, and it doesn't really matter. The entropy did go up, always and always does, if you take into account all of the heat transfers and all of the temperatures, even if the temperatures do change. Here we have work output of Carnot engine between two temperatures. Transfer the engine, suppose this produces energy. So essentially what we're doing is we're taking the previous example and we're using it inside of a Carnot engine. So we're using a Carnot engine between those two temperatures with that same flow of energy, flow of heat, and they calculate the efficiency at 0.833 for the Carnot engine, and